Hello, I want to take a moment and talk about Atik AI Accelerator, how it is built and why it is built actually. This is a series consisting of two videos. The first one is going to talk about the software stack, the one that you are watching right now, and it actually talks about a little bit of the hardware stack. However, in the next video, you can see that we are talking about the whole architecture in a conceptual view, and also we are gonna debug some waveforms and delve deeper to the hardware architecture. For now, I just wanted to show you this the repo and the project as a whole. So if you are really interested, you will watch the rest of the videos, in my opinion. So there's a lot of companies now trying to develop AI hardware from accelerators to edge devices, but there is so little information about how to build this technology in an open source manner. There are, of course, accelerators that are open source, AI accelerators that are open source, but they are too old. None of them actually really support attention. Even if there are some, they don't build on real microarchitectures like Rocket Chip, or they don't include PyTorch bindings, etc., etc. You can see why this project is built here, and also some of benchmark results. Now, these are maximum performance obtained on these benchmarks. So as big as the problem gets, as bigger mesh sizes, bigger matrix sizes, the more speedups that we gain. And I have run tests up to, until a certain size, because after that it started to take too much time on the even on FPGA. And this is actually a basic layout on how matrix multiplication modules, how attention modules, SRAMs are actually laid out on the chip. And this paragraph here really tells why this project is built and for who it is built. These are the cells that after a lot of optimization iterations, they settled in this position. Now coming to the simulation and running the project itself, it is built on Chipyard framework, and Chipyard helps building chips like you can imagine. So you need to install that framework, you need to set up that framework, you need to follow their instructions. Also, because it is an accelerator that is in that framework, there are a couple of bindings that you should do, and you should be good to go. After that, this verilator setup is for 2x2 rock config. If you need to see other results, faster results, you need to try the 4x4 rock configs. And even more, if you have access to AWS FPGAs, you can run the bigger tests in much less time. This is about how speedup is calculated. Because we are taking Rocket Chip as the baseline, we use this way. You can check the C code. The architecture is more detailed in a markdown way, in a more readable way for you or for your agent under the manifest directory. Now coming to the time and cycle accurate simulations, we can see that for these workloads, the speedup we have obtained with respect to the baseline are like the following. I want to stress that these are for different hardware sizes. You can see that as long as the mesh size increases from 2 to the 4 to the 8, the more hardware speed up we get, and the more complicated the problem, the bigger the problem size is, the more speed up we get. And aggregate actually means the total CPU amount divided by the total accelerator amount. So you can see how much speed up you get if you use the accelerator and not use the CPU. And this is peak performance. So imagine you got a lot of tests with different sizes. What is the maximum performance that I can get? So these results will give you a high level idea on how this accelerator is actually performing with respect to the CPU core. These actually are much more detailed results. So for example, for Atik 8x8 on the TinyBird workload, you can see that for bigger matrices and bigger modules, it starts to get much more faster than the regular one, than the CPU, the Rocket Core one. And these results are like, as you can see here, You can obtain really high speed ups with this simple architecture. Actually, it is simple because there is Grok, there is Cerebrus, there is so closed source projects that are much more complicated. However, even this simple one can gain so much high speed ups over the baseline. So, and this is actually the layout of the modules, how attention engine, which is actually attention controller, and the matmul controller really lays out on the chip, how our B SRAMs, A SRAMs, and Q SRAMs actually lay out on the chip. You can see them here, and other details for the VLSI flow. So if you are interested in this project and you find it useful and helpful, you can continue watching the rest of these videos. However, if it didn't catch, you can close the same things here. Thank you for your time and have a great day. Alright, welcome back. We will start building from the software stack, then we'll go to the hardware stack, and we will see how the software will limit actually the hardware and define the interfaces needed for the hardware to do what the software tells it to do. And first thing first, we need to define our microarchitecture. And we need actually to use a ready microarchitecture to build on top of and enhance. And I'm going to use actually a microarchitecture called a rocket chip. And this rocket chip is a microarchitecture built by UC Berkeley. And one of its main advantages that it allows you to actually add an accelerator to it. So it reserves a place called Rocket Custom Coprocessor, or briefly ROC, that is actually a tightly coupled accelerator. We will build that tightly coupled accelerator and attach it to this microarchitecture. Now, this microarchitecture actually builds or implements the RISC-V instruction set architecture and also its own communication protocol, which is called Tile. And we will use this ecosystem to build our own AI accelerator and attach it to this microarchitecture and make AI workloads really fast. Now let's imagine that we have an accelerator, and let's call it Atik, which will actually refer to the final work that we will build by the end of this series. And this Atik is gonna be a Rocket Custom Coprocessor, just like this guy. And let's try to think about how this Atik will communicate with the outside world. It has actually two options, two possibilities. First, it will directly access the L1 cache or any kind of memory block. And by doing that, we are actually having a great flexibility because I don't need to go through the core itself to access the outside world. However, we can do that also. Let's do that now. So because we are using this specific microarchitecture again, we have the ability to access the core right away. And this core is called a rocket core. So I'm gonna just write core right here, as you can see. And because we have so many ways of communication, and we have so many combinations, and we have so many hardware modules to communicate with, we need a specific protocol to access the memory. So imagine Atik wants to access a specific pointer of data, and the core actually wants another thing. Some of them will write, some of them will read. Somebody need to orchestrate that. And that orchestrator is also the built-in support for communication, which is called tiling. All right, now we should think more about how me, the user, I'm just sitting right here writing my RISC-V assembly code. I will send it to the core, and the core must figure out a way to send this specific instructions to the accelerator. And this way will be by using a specific queue called the command queue, and the command queue will directly go to the accelerator this way. So this is the command queue, and the accelerator will respond to that to each command it receives through another queue that we'll be calling the response queue. Now, after we have reasoned about how should the modules talk with each other and the interface between the accelerator and the core itself, we can now think about the instructions. and which instructions are going to trigger this specific accelerator. So because we are dealing with RISC-V instruction set architecture, and because we are using the rocket ship microarchitecture, we have specific instructions that are reserved for us. So funct7, because our accelerator will have so many functionalities, we should specify which functionality are we expecting from it. So imagine that the first functionality, which we are going to talk about in a bit, which will set the description. So it will actually configure, it will configure what the accelerator should do, and one will run that configuration. Two can be used to retrieve the statistics about the accelerator that we are saving in the registers, for example. So let it be stat. Three can just shut down the accelerator, reset the accelerator. Depending on the condition, depending on what we are doing, we may be using all of these three registers. We are maybe just using two registers, and depending on the combination that we are doing. So for example, we are always going to use all these three registers. We should specify in the funct3 that we are using all of them, which will be encoded by the following 111. What this first one describes or says that we are using RS2, this one is RS1, and this one for the return destination register. And finally, the this core might be attached to so many accelerators. We need to specify which accelerator are we sending this instruction to. All of these are specific opcodes reserved for certain accelerators. So imagine you have three accelerators attached to your microarchitecture. Because we are going to use just one, we will just use the custom 0 opcode, and which actually refers to, if I remember correctly, 001101. Now I guess it is a good time to take a look at the code and see how we actually implementing these instructions and what kind of instructions we are supporting in this accelerator. So you can see here that these are actually the funct7s that we have talked about. So we have a couple of functionalities. The first one is for setting the description, running that description, getting the stairs, etc. And one of the most important things that we need to define in the instruction is the opcode. And what I mean about the opcode is which accelerator we are actually sending instructions to. And if you come to the hardware code, hardware chisel code, you can see here that for whatever config that we are running, either the mesh size of 2 or 4 or 8, we are actually having the same opcode, which is custom 0. So you can see here that the custom opcode value, which is 0 at the moment, you can see it, it is actually in each instruction that we are going to send to Atik. So this is a macro, and this macro's job is to convert the inputs, which are the register addresses, and which functionality we are using, and returning a valid assembly instruction. So for example, if I want to set a description, given a description pointer, which we will be briefly talk about what are we describing, we need to call this function, and this function uses this macro to actually construct our instruction and eventually send it to the accelerator. Now that we know how to create instructions, how to send these instructions to the accelerator, and how the core actually decodes these instructions, we can start to think about how we should formulate this problem for the user, so the user is absolutely abstracted of any kind of algorithmic solutions. So what I'm trying to say is, for matrix multiplication or attention mechanism calculation, you have a lot of optimized algorithms. However, the user should not implement these algorithms in the software stack. The hardware should figure out how to calculate these matrices and how to solve them in the most efficient way without the user having anything to do with the algorithm. So imagine we have a matrix A, and we're going to multiply it with matrix B to actually store the result to the matrix C. And we know that matrix A will belong to M to the K dimension, and B will belong to the K to the N dimension, and eventually C will belong to the M to the N dimension. Also, we know that the heading dimension of A is M, the heading dimension of B, actually let me just use the laser pointer here, and leading dimension of A is M, the leading dimension of B is K, and the leading dimension of C is M. Now the leading dimensions are important for us in the hardware, so we can tile over these matrices in an efficient manner. So the user basically will just expose the pointer to A, the pointer to B, and the pointer to C as a matter of data. Also, it will give us the M, K, and N values, so we can know how much big are the matrices that we are dealing with, and which are the leading dimensions. Other than that, we don't need anything from the user. And because our accelerator will actually do more than matrix multiplication, it will also calculate attention. We should also take the scenario of attention mechanism, not just formulating the math model will be enough for us in this case. So we need a Q matrix and we need a K matrix which will be transposed. Then we will actually normalize this by the dk, which is the ddim, and we will take the softmax in a specific dimension that we will actually, for convenience, with the 0th dimension, and we will take the softmax. Then eventually we will multiply by the value matrix. We already know how to matrix multiply, but because if you actually suppose that we implemented this side of the problem, we know how to multiply two matrices. The new thing that we must introduce for the attention now is dividing, and we will implement this using lookup tables. You can do other numerical methods, however, for the sake of simplicity and to be fast, I will just use lookup tables. So we expect this also from the user. We will also calculate the softmax. And softmax is kind of tricky here because these matrices are so huge and we cannot put all of them in the accelerator. We should have a way to do a softmax. So online softmaxes say it is the algorithm that has been used in the flash attention paper, and we will implement online softmax. What online softmax means, imagine we have a big two matrices, 512 by 512, and we will multiply both of these because we will have small registers like that will fill 32 by 32 matrices. We will actually need a way to tile over these matrices and compute softmax on the fly. We will also do the same thing for the matrix multiplication. You can imagine it as online matrix multiplication. So to summarize here, what we need from the user, we need also the dimensions of these guys, and we also need this as an input, and that's it. We now defined what kind of inputs we need from the user to calculate either a matrix multiplication operation or attention mechanism, and we will see how that is implemented in the code in a bit. Alright, now let's take a look at the software and how are we actually sending instructions to the accelerator by looking at a real workload. So when you go to the repository, you will see software directory, and under software directory, you should go to the source to see a couple of workloads that we are supporting. If you go to the smoke, and it is actually smoke testing, you can see that we are running under the main two basic smoke tests. The first one for matrix multiplication and the other for attention. Going to the matrix multiplication, we first multiply in reference mode. What I mean in reference mode is without using the accelerator itself, we will see how the result is calculated by the CPU, and this will be our ground. Then what we really care about now is how the accelerator is really multiplying and how are we sending the instruction to it. So going into that function, you can see that we first validate these dimensions. So we are sending to the accelerator basically the pointer of A, the pointer of B, and because it is a map mode, there is no V matrix, you are passing 0. And one of the important things is that we are saying to the accelerator, yo, you should do now matrix multiplication, because we support other operations as well. We support mapmul, we support attention, we even support causal attention. And so going back to the descriptor, you can see that we also passing the output matrix, its address, it is allocated and ready for use. One important thing one other important thing is that we are casting the addresses to be 64. That this will make it easier for us to implement in the hardware. Then we have these dimensions that we have talked about earlier, which has M, N, and K, and we have the leading dimension of A and B, even C, and the other arguments that are specific for attention we don't care about much at this moment. And we submit this description to the accelerator. Now, by submitting this description, what we mean is we have two passes, two actually instructions are being sent to the accelerator for doing this workload. First, we are setting the description. We have this huge struct. It is not that huge. It is 128 bits, 128 bytes, if I remember correctly. We are sending it to the accelerator and telling it to store it in its registers. Now, after the accelerator says everything is okay, I have stored the description, just tell me when to run it, we will send the rock run instructions. So it is in two phases. We first just describe the problem and then tell the accelerator to solve that problem. And if we go to the Atik rock set description, we will go to the old file that I've shown you earlier when we are trying to figure out how should our instructions be constructed. And we now here have actually two instructions to run for a single workload, like I have said. Now we're gonna run that matrix application, and actually it has a specific funct7 code, which is coded in 0 and in 1. So to summarize things, we set the description that we want the accelerator to do by using that funct7 equal to 0 and funct7 equal to 1. We use to do a single workload, we have two instruction calls, which is so minimal. And this actually here is used for the sake of counting the cycles in the right way. We put a fence. This fence tells the rocket chip to not ever pass this instruction until it is finished. Because we are calculating how much cycles that this instruction consumes from the chip itself, we need to put this fence so it doesn't pass it and we get wrong cycle counting. Now let's take a look at the attention workload. How are we actually asking the accelerator to do attention? It is quite similar. We have a reference attention and we calculate the cycles that have been used or consumed by the regular CPU for calculating attention, and we are doing the same but this time for the accelerator. Going to that function, we can see that the accelerator now runs this attention with a specific descriptor that now uses the QKV matrices. One of the important things is that the scale BF16, like I have said, the square root BF16 value, which is DK, is also sent to the accelerator for it to normalize after QKT multiplication.